Hello and welcome. In this lecture, we're going to take a broad overview of the use of spectral Doppler in echocardiography. The start of this lecture is going to be pretty physics heavy, but if you can make it through those opening sections, we're going to get much more practical, and we're going to discuss how to obtain the most reliable measurements, and then we're going to finish by looking at some of the most common applications such that you can start putting these techniques into practice. We've touched on the Doppler principle previously, as part of our Level 1 series, when we discussed the generation of colour maps. I've debated the idea of referring the audience back to that video before watching this one, but ultimately I've elected to create a lecture that stands alone. So if you've never seen that lecture before, then I definitely recommend that you check it out, but it's far from mandatory. Necessarily, this means that there will be some overlap between that previous lecture and this, but hopefully the descriptions here will serve as useful revision rather than being tediously repetitive. Okay, let's get on with it. So when we're considering the application of the Doppler effect in cardiac ultrasound, we are exploiting the phenomena whereby the sound wave that our probe generates experiences a shift in frequency if it reflects off a surface that's moving relative to our probe. Now, for our purposes, that reflective surface is usually blood, not always, and we'll come back to that later, but it's usually blood. So let's imagine we have three probes which are transmitting ultrasound waves towards the three columns of blood. Each probe is emitting a wave of identical frequency. We can imagine that these green arrows represent wavefronts, perhaps a wave of maximum compression. Now, if the sound waves are striking blood which is stationary, then the reflected wave returns to the probe unchanged. The transmitted frequency is identical to the returning frequency. If the blood is moving towards the probe, then when the sound is reflected, the amount of time that elapses between each wavefront from being reflected becomes shorter. The wavefronts are moved closer together, the frequency increases. The magnitude of this change in frequency is directly proportional to how quickly the reflective surface was moving towards the probe. Likewise, if the reflective surface is moving away from the probe, then each wavefront strikes the reflective surface slightly later, and the wavefronts start to spread out. There's a greater temporal gap between each wavefront, and therefore the frequency of wavefronts decreases. The frequency of a returning wave is now lower than that of a transmitted wave. The relationship between the velocity of the blood and the magnitude of a frequency shift is described in the Doppler equation. Let's break this equation down in order to understand it. In this equation, f0 represents the frequency of a transmitted wave, the frequency that the ultrasound probe initially generated, and of course the ultrasound machine knows this value. Delta f is the observed shift in frequency, that is, the difference between the frequency that the probe generated and the measured frequency of the returning wave. C represents the speed at which the ultrasound wave was travelling. Now you may recall that sound will travel at different speeds through different materials. But for the purpose of generating 2D images, the ultrasound software makes the assumption that sound wave is travelling at 1,540 meters per second, which is the value we use to represent the average speed of sound through soft tissues. When we're performing Doppler techniques, we make this same assumption, so we use a value of 1,540 meters per second in this equation. Theta represents the difference in alignment between the ultrasound beam and the direction of motion of a reflective surface. So, if the ultrasound beam is directed such that it's striking the reflective surface head-on, then the angle of intercept will be 0 degrees. If the moving structure is moving perpendicular to our ultrasound beam, then the angle of intercept will be 90 degrees. In cardiac ultrasound, we go to great lengths to ensure that the direction of the ultrasound beam is aligned as perfectly as possible with the motion of the part of the heart that we're interested in. When we're using the Doppler equation, we assume that theta is 0 degrees, and the cosine of 0 degrees is 1, so for cosine of theta we can use the value 1. We can now rearrange the equation in order for us to calculate the velocity of a reflective surface by inputting both the known transmitted ultrasound frequency and the measured frequency of a returning wave. When we perform Doppler assessments within the heart, there are two main ways we can do this. We'll start by looking at continuous wave Doppler. In this technique, a portion of the ultrasound crystals within the probe are continuously generating a wave of a known frequency. The remaining crystals are acting as continuous receivers, waiting to generate current when they're struck by returning waves. The ultrasound wave passes into the body and encounters structures within the body as it travels. Some of these structures will be effectively motionless, whilst others will be moving. As we know from having studied basic ultrasound physics previously, the majority of the transmitted energy passes through the soft tissues it encounters. However, a small amount is reflected back towards the probe. When generating a 2D ultrasound image, our crystals vibrate only momentarily, generating the wave that travels into the body, and then they switch to a receiving mode, waiting for the returning reflected sound. The ultrasound machine knows the speed at which the wave is moving through the tissues, and so it can work out where in space the reflective surface is, based on how long it took for the reflection to return. Contrast this with continuous wave Doppler. In this technique, there are crystals that are dedicated to wave generation continuously, and there are other crystals dedicated to continuously listening. A returning signal may be a reflection from a superficial structure that was struck by a wave that has only just been generated, or conversely, the signal may be from a deep structure that is reflecting a wave that was generated relatively long ago. The ultrasound software is unable to differentiate between these two possibilities. Therefore, when using continuous wave Doppler, we can estimate the velocities of many different structures along the path of the ultrasound beam, but we don't know exactly where in the heart those reflected waves are coming from. Contrast this with pulsed wave Doppler. When using this technique, we specify a region of interest by placing a small box, often referred to as a sample volume, and then ask the ultrasound machine to provide velocity information relating to only this area. Now, rather than generating ultrasound continuously, the probe generates a short burst of ultrasound, typically between 1 and 2 microseconds in duration, and then switches to a listening mode, waiting to receive reflected waves. How long the probe must wait between bursts is dependent on how far the sample volume is from the probe. Let's imagine that we use a sample volume that is 6 mm deep and placed so that the center of the sample volume is 100 mm from the probe. We're now asking the ultrasound machine to look for a signal returning from a depth of between 97 mm and 103 mm. In this example, the probe fires a burst of ultrasound and then switches to a listening mode. We're interested in those reflected waves which have travelled a total distance of between 194 mm and 206 mm, because that's the distance required to reach our sample volume and then make the way back to the probe. Now we know that the average speed of sound in soft tissues is 1,540 meters per second. This means that any signal returning prior to 126 microseconds must have reflected off of a structure that is closer to the probe than our region of interest. Likewise, any returning signal that arrives later than 134 microseconds must have reflected off a structure that is deeper than the far limit of our sample volume. We can see now how the depth of the sample volume dictates how frequently the probe can generate new bursts of ultrasound. In this example, the probe must wait at least 134 microseconds before generating a new burst of ultrasound. We refer to this duration as our pulse repetition period. We can now calculate the maximum possible number of pulses that can be generated in 1 second, which is our pulse repetition frequency. So in this example, our pulse repetition period is 134 microseconds, which means that the most pulses we could possibly generate per second is 7,462. Our pulse repetition frequency is 7,462 Hz. Understanding that pulsed wave Doppler necessarily has a maximum pulse repetition frequency allows us to understand the principal limitation of this technique, which is aliasing. Aliasing is the phenomenon whereby the returning signal is sampled infrequently, such that we can no longer confidently reconstruct the signal from our samples. In order to be able to correctly identify a wave, we need to sample it at least twice per period. This can be a tricky concept to get your head around, so let's take a look at a commonly cited example that demonstrates this quite nicely. Let's imagine that we're sat in a room with a clock which has only a second hand. The clock is working correctly, so the second hand rotates in a clockwise direction, taking 60 seconds to complete one rotation. Now, if we glance up at the clock every 5 seconds, we'll notice that the second hand has moved, and we will not unreasonably assume that the second hand is rotating in a clockwise direction and at a rate of 30 degrees every 5 seconds. And in this scenario, we would be correct. The second hand is rotating once per minute, and we're sampling the clock 12 times per minute. So we're sampling the clock with an adequate frequency to correctly identify both the direction of rotation and the speed of rotation. But what would happen if we glanced at the clock less frequently? If we glanced once every 25 seconds, then we could still correctly determine the direction and speed of rotation. But if we sample the clock every 30 seconds, well, now the second hand appears to oscillate between two positions. We can be certain the second hand is moving, and as we can see that it always points straight up every 60 seconds, we can imagine that it's rotating once per minute. But we can't be certain whether it's rotating clockwise or anti-clockwise. If we glance at the clock every 35 seconds, we're now sampling with a frequency of less than twice per period. The hand is rotating clockwise, and is rotating 210 degrees every 35 seconds, but we might easily confuse this with a slower anti-clockwise rotation. Indeed, we might imagine that the hand is rotating anti-clockwise at a rate of 150 degrees every 35 seconds. Because our sample frequency has dropped below twice per period, our interpretation of the returning signal has become inaccurate. Let's imagine a different example. Let's imagine we have 3 clocks side by side, and the clock in the center is working normally. The second hand rotates clockwise once per minute, but the clock on the left and right are both broken. The clock on the left has a second hand but rotates anti-clockwise 3 times per minute, whilst the clock on the right has a second hand but rotates clockwise but 5 times per minute. If we glance at all 3 clocks once every 15 seconds, then the hands will be in identical positions each time we check. With this sample frequency, we won't be able to distinguish which clock is working properly and which clocks are broken. In order to be certain how the hands are turning, we must watch the clocks continuously, and then the true speed and direction of motion is revealed. This is the key difference between continuous wave and pulsed wave Doppler. With continuous wave Doppler, we can identify many different velocities accurately, but we cannot be certain where along our ultrasound beam path those velocities are occurring. Whereas with pulsed wave Doppler, we can know where the returning signal has arisen, but there's an inherent maximum speed limit, and velocities that exceed that speed limit are misinterpreted, both in terms of the magnitude of velocity as well as the direction. So what is the practical speed limit when using pulsed wave Doppler in echocardiography? In order to estimate our maximum speed limit, we need to introduce a new term, the Nyquist limit. The Nyquist limit is the maximum frequency shift that can be accurately measured and is equal to half the pulse repetition frequency. The pulse repetition frequency is dependent upon the distance between the probe and the sample volume. Therefore, the principal determinant of the speed limit is how deep we place our sample volume. Let's take a look at an example. So here we have an apical 4-chamber view, and we're trying to measure the velocity of the blood as it leaves the left atrium and enters the left ventricle. We are using pulsed wave spectral Doppler, and we've placed our sample volume just inside the left ventricle, level with the mitral valve leaflet tips, when they're maximally open in diastole. Let's imagine that our sample volume is 100 mm from the probe and has a height of 4 mm, so the farthest aspect of the sample volume is 102 mm from the probe. We can then calculate our maximum possible pulse repetition frequency, which comes out at 7,549 Hz. This would make our Nyquist limit 3,774.5, so half of our pulse repetition frequency. So in an ideal situation, this would be the maximum phase shift we could accurately detect. To calculate the velocity that would produce that phase shift, we would need to know the frequency of the emitted wave. The lower the frequency of the emitted wave, the greater maximum velocity we may be able to detect. The emitter frequency may vary between different ultrasound machines, and on some higher end ultrasound machines, this information may be displayed on the saved image. On the equipment that I most commonly use in my own practice, the ultrasound machine uses a wave with a transmitted frequency of 1.6 MHz. So let's substitute that value into the equation, and this suggests that we should be able to accurately detect a velocity up to 181 centimeters per second. Not only that, but we should be able to accurately determine the direction of that velocity, as long as it doesn't exceed that limit, whether it's either moving towards or away from our probe. Now, in reality, the pulse repetition frequency the ultrasound machine generates will be slightly lower than this. And my best guess for why this happens is that there must be a small amount of processing time between each burst. I used my own ultrasound machine to try to reproduce this, and with these settings, the maximum velocity I could detect was 126 centimeters per second. This suggests that the true PRF being used in this case was actually just 5,236. So in this test, I could only achieve a PRF of about 70% of the theoretical maximum. We know that the Nyquist limit is dependent upon the depth of the sample volume. The further the sample volume is from a probe, the longer the ultrasound needs to wait between pulses. So what happens if we drop the sample volume down into the far field and place it over this pulmonary vein? Now the furthest edge from our sample volume is 193 millimeters from our probe. This drops the Nyquist limit down to 1995. Using a transmitted frequency of 1.6 MHz, we might hope to detect velocities up to 96 centimeters per second in either direction. In reality, when I tried this on my own system, I could get velocities of 81 centimeters per second, but not higher. The maximum velocity we might hope to achieve in theory is never achieved in reality. Given that many of the pulsed wave Doppler measurements we make in adult transthoracic echocardiography are approximately 10 centimeters or so from our probe, in practice we can usually only accurately measure velocities up to about 1 meter per second. Alright, so now we have a sense of how velocity data is captured, we need to take a look at how it is displayed. So here is a typical continuous wave Doppler graph. Let's take a look at what information is displayed. So at the top we have a still 2D image, and we can see that this is taken from an apical 5-chamber view with the cursor lined up to pass through the left ventricular outflow tract and aortic valve. Almost certainly the highest velocities we will record will occur during systole when the blood exiting the left ventricle passes through the aortic valve, and with our cursor in this position we hope to pick up those velocities. But we should remember that we're going to pick up velocities along the entire length of the cursor, so in this case that mostly means other blood flow within the left ventricle. Below this we have our continuous wave Doppler graph, with the patient's ECG overlaid. Our x-axis is time, and the scale of the x-axis is referred to as the sweep speed. Here we can see that our sweep speed is set to 75 millimeters of screen per second of time. Now this can be adjusted depending on how many cardiac cycles we wish to display. The range of sweep speeds available to us typically ranges from about 25 millimeters per second to 200 millimeters per second. We can choose a slow sweep speed, like 25 millimeters per second, if we need to demonstrate as many cardiac cycles as possible, and we might wish to do this to demonstrate variation over time, particularly variation with the respiratory cycle. We choose a fast sweep speed, like 200 millimeters per second, if we only need to show 1 or 2 cardiac cycles, but we want to make them fill the available screen space to improve our accuracy when measuring manually. In this still, our patient is in atrial fibrillation, with quite varied cycle lengths, resulting in beat-to-beat variation in flow velocities. By choosing a middling sweep speed of 75 millimeters per second, we can display approximately 5 cardiac cycles, which highlights the variability which is present. Our y-axis is apparent velocity, the speed at which the blood is either moving towards or away from us. This brown line is our baseline and represents no movement. By convention, we record movement towards the probe as above the baseline and movement away from the probe as below the baseline. We can see 5 pointed triangles below the baseline, and these occur after each QRS complex and represent the blood exiting the left ventricle during systole. We refer to these triangles as envelopes, and in continuous wave Doppler they're filled in or solid. Let's take this fourth envelope and assess what's happening. We see our QRS complex, and ventricular systole is initiated, and as the LV contracts, blood is pushed towards and through the aortic valve. At any given moment within systole, the leading edge of this envelope represents the fastest moving blood, which in this case will be the blood moving through the open aortic valve. But we will also be receiving velocity information from just immediately prior to the valve, where the blood will be moving quickly, just not quite as quickly as the blood that's passing through the valve. We'll also be receiving velocity information from blood within the outflow tract, and blood approaching the outflow tract, and blood moving within the centre of the LV cavity. All of this blood will be moving at different and slower velocities, so we end up with many different velocities all occurring simultaneously and being displayed simultaneously, hence our filled in envelope. There's other information being displayed here as well. There are intense signals at the start and end of each LV ejection, and these clicks represent the opening and closing of the aortic valve. We can see signal above the baseline during diastole, and this will be blood refilling the LV during diastole. Let's contrast this with a pulsed wave Doppler graph. So this is the same patient, but here we are looking at LV inflow. From the apical 4-chamber view, we have a cursor that passes from our probe down through the left ventricle, across the mitral valve and through the left atrium. But in this instance, we have a 4 mm sample volume just inside the left ventricle, level with the mitral valve leaflets when they're open. On our thumbnail image, this sample volume appears as two parallel lines, but different manufacturers use different graphics to display this. Now, we're recording only information returned from a specific region of interest. We're recording the speed of blood as it passes through the sample volume, but we're not recording velocity information from blood as it enters the mid-LV cavity and slows down. This leads to our envelope being hollow. In addition to losing slower speeds, we might also be missing greater velocities. If our intention was to detect the fastest velocity that occurs, then if our sample volume is not in the perfect spot, we might miss it. As a general rule, when your priority is to know about the speed of blood in a specific location, then you should use pulsed wave Doppler. When your priority is to identify the greatest velocity, irrespective of where it occurs, then you'll wish to use continuous wave Doppler. Whilst discussing pulsed wave Doppler, we spent some time discussing the phenomenon of aliasing. Let's compare some Doppler graphs from our patient to see how this appears in practice. So our patient has severe left ventricular systolic impairment with some mitral regurgitation. If we place our cursor through the mitral valve and create a continuous wave Doppler graph, we will capture both the antegrade LV filling during diastole as well as the retrograde mitral regurgitation occurring during systole. Now, for reasons that we'll cover in a minute, LV filling is typically not that fast, usually somewhere around 60 to 100 centimeters per second, rising above that in some specific circumstances. By contrast, MR is usually just about the fastest blood velocity that we record, and here in this patient we can see that it's reaching close to 4 meters per second. When using continuous wave Doppler, we can record and display all of the antegrade and retrograde flow without aliasing, as for our purposes, there is no upper speed limit. Now, if we then compare that to a pulsed wave Doppler graph, we can see our LV filling accurately displayed, but during systole we have these solid blocks of velocity data, as the blood is travelling far too quickly to discern either velocity or direction of travel. This is the pattern we see when the velocity is more than double our speed limit, but aliasing is not always as dramatic as this. This example is taken from a transesophageal study, and is a deep transgastric view looking at the left ventricular outflow tract and blood leaving the left ventricle. If you're not familiar with TOE, don't worry, the physics is identical, and you can think of this as very similar to an apical 5-chamber view in a TTE. This is pulsed wave Doppler set up in such a way that we have a pulse repetition frequency of 7,230, hence our Nyquist limit is 3,615. And a maximum discernible velocity of 96 centimeters per second. That means we can accurately discern blood velocity in either direction, either towards the probe or away from it, up to 96 centimeters per second. At the onset of systole, the blood within the sample volume starts to move away from a probe, and for the majority of systole we can track this. However, there comes a point just prior to the peak velocity when the observed frequency shift reaches our Nyquist limit. At this point, the velocity is known, but the software cannot differentiate between blood moving away from a probe or blood moving towards a probe. In our example of the clock with only a second hand, this is equivalent to when the clock hand is oscillating between two opposite positions on the clock face. As the blood then accelerates further and produces frequency shifts which exceed our Nyquist limit, our software starts to incorrectly register velocities in the wrong direction, which appear to slow down rather than speed up. By the point at which the maximum velocity is reached, the true velocity is 116 centimeters per second. This is 20 centimeters per second above our speed limit, but the ultrasound system tells us that we're seeing a velocity 20 centimeters below our speed limit, and in the opposite direction. When we're in this situation, when the velocity exceeds what we can measure, but by less than double, we can get around this by telling the ultrasound software which direction the blood is moving in. We do this by adjusting our baseline, so this graph is identical to the previous graph, but the baseline has been shifted towards the top. We are telling the ultrasound software that we know the blood is moving away from us. In our clock analogy, this is equivalent to knowing that the hand is rotating clockwise. Now, rather than imagining that it's turning anti-clockwise slowly, we can know that it is turning clockwise quickly. By adjusting the baseline, we can effectively double our speed limit. In practical terms, this means that if we know the direction of blood flow, it's usually possible to track blood velocity up to around 2 meters per second, but not beyond. Okay, so whenever we are performing an echocardiogram, we need to optimize our images in order to improve our accuracy and obtain the most information possible. This is true when we're using 2D, M mode, and color Doppler, and it's equally true now that we're adding Spectral Doppler to our toolkit. And just as we have a sequence which we follow when we're producing a 2D image, there are steps I would advise my trainees to take when producing Spectral Doppler graphs. So the first step is a constant throughout all of echocardiography, and that is try to achieve the best possible 2D image. In part, this will help you ensure correct cursor placement, but also if you have a clear 2D image with minimal artifact, then you're going to produce a clearer spectral Doppler graph. The reflected ultrasound that is used to produce a 2D image is the same reflected ultrasound that will provide you Doppler information, so anything that hampers your 2D image will also hamper your Doppler. Next, you will often wish to place a color box over the area that you're interested in. This will provide you with a visual representation of the flow of blood, and in most instances, you'll want to align your cursor with the color flow. Remember, color flow is a form of pulsed wave Doppler, just represented as 2D or 3D color rather than as a graph. So if you have poor quality color images, then you're very likely to have issues with your spectral Doppler. Once you've lined up your cursor, consider the difference between the path of the cursor and the path of the blood flow. You want to ensure that these are as well aligned as possible, and that you have minimized malalignment. If we look at this simulated apical 5-chamber view, we can see that there's a difference between the path of blood flow and our cursor. Why is this an issue? Let's imagine that this man is trying to estimate the speed of a ball as it moves around him. He fires waves of sound towards a ball, and then measures the frequency shift of a wave as it returns to him. Whilst the ball is clearly moving, the distance between the man and the ball never changes, so the wave that he transmits returns unchanged. If he is relying on the Doppler effect to estimate velocity, then he will conclude that as the distance between himself and the ball never changes, then the velocity is zero, and that the ball is not moving. Let's look at another example which allows us to quantify the impact of malalignment. Here the man is looking straight as the car passes in front of him. As it passes directly in front of him, the car is travelling at 9.2 meters per second. Let's imagine that it crosses his field of view in 100 milliseconds, so a tenth of 1 second. So it's travelled 92 centimeters during that moment. But not all of the motion is directed towards the man, and so whilst the car travels 92 centimeters, it finishes only 65 centimeters closer to the man than it began. Again, using reflected sound waves and the Doppler effect, this would cause the man to underestimate velocity. Using the Doppler equation, we can approximate how much we are underestimating the true velocity. The difference between the angle of motion and the angle of our ultrasound beam is termed theta. When the angle of motion and the angle of observation are the same, then theta is 0 degrees. The cosine of 0 degrees is 1, and so our calculated velocity is 100% of the true velocity. When the car passed in front of a man, theta was 45 degrees. The cosine of 45 degrees is approximately 0.7, so our calculated velocity is approximately 70% of the true velocity. This is why, whilst the car was travelling at 9.2 meters per second, the man estimated the speed of the car at 6.5 meters per second. If the angle of motion is at right angles to the angle of observation, then theta measures 90 degrees. Then, as the cosine of 90 degrees is 0, then the measured velocity will also be 0. This graph demonstrates how the angle of theta impacts on how much we underestimate the true velocity. When the angle of intercept is only a few degrees out, then the magnitude of underestimation is relatively small. However, this inaccuracy rapidly increases the values of theta above 20 degrees. In vascular ultrasound, the blood is travelling within a pipe. Flow is laminar, and the direction of flow is predictable. Therefore, it's reasonable to apply a correction factor in order to overcome this underestimation. Here we have pulsed wave Doppler of the axillary artery in a patient in whom I was setting up to site an axillary arterial line. Eagle-eyed viewers might notice that there are 2 pulses per cardiac cycle, and that's because he was being supported with an intra-aortic balloon pump, which inflates during diastole, producing this second early diastolic pulse. Using pulsed wave Doppler, we can measure a peak blood velocity of 43 centimeters per second. But there is a significant difference between the angle of the ultrasound beam and the angle of the blood flow, such that we know we're underestimating the true velocity. In vascular ultrasound, we might therefore apply an angle correction. In this second image, I've told the software that there's a malalignment of 70 degrees. It therefore knows that we're underestimating the blood velocity by about 2/3, and so it applies a correction factor which allows us to better approximate the true blood speed, which here comes out at 135 centimeters per second. This technique is acceptable in vascular ultrasound, where the blood flow tends to be laminar and the blood is moving along a single known plane through a vessel with parallel walls. The same cannot be said for flow within the more geometrically complex heart, and therefore angle correction is not applied in echocardiography. The next consideration relates to the sample volume, and therefore applies only to pulsed wave Doppler. When learning this technique, it is reasonable to know that the size of the sample volume can be adjusted. A small sample volume allows for greater precision. However, the amount of returning signal will be proportional to the size of the sample volume. So if a returning signal is weak, you may need to increase the size in order to produce a stronger signal. In my own personal practice, I very rarely need to adjust the sample volume size. The different machines that we use within our department default to a sample volume size of 4 to 5 mm, and this appears to be adequate for most applications. Out of interest, whilst preparing for this video, I used pulsed wave Doppler within the left ventricular outflow tract using sample volumes of 1 mm and 10 mm. And in this single example, personally I can't really see a particularly significant difference. Indeed, if you look at the image on the right, which has got a slightly broader edge of the envelope, slightly brighter with more noise, actually this is the image that was taken with a sample volume set at just 1 mm, and the image on the left was captured using a sample volume of 10 mm. Perhaps the opposite of what I might have expected. Something that you certainly will need to pay close attention to, however, is sample volume placement. As blood passing through the heart can sometimes rapidly slow down and speed up, moving the sample volume just 5 to 10 mm can have a dramatic effect on recorded velocities. Let's take a look at an example. Let's imagine that we want to assess the speed of blood leaving the left ventricle via the outflow tract. Here we have the apical 5-chamber view of a healthy volunteer. If we zoom in on the outflow tract, we can see how the aortic valve moves apically during systole. So an important consideration is that when we're using pulsed wave Doppler, the sample volume remains in a fixed position, but the heart will be moving around it. Okay, so let's now add colour, and we can begin to place our sample volume. Here I've recorded pulsed wave Doppler graph for 3 sample volume positions, each slightly closer to the aortic valve. This first graph is recorded with the sample volume at a depth of 8.4 centimeters. and at this point in space, the blood travelling towards the valve reaches a maximum velocity of 78 centimeters per second. If we then advance the sample volume so that it is at a depth of 9.1 centimeters, so 7 millimeters closer to the valve, we now record a maximum velocity of 96 centimeters per second. Finally, we can advance the sample volume to a depth of 9.5 centimeters, which is just 4 millimeters further, and now the peak velocity has risen to 109 centimeters per second. Our first and third graphs were recorded with the sample volumes placed just around about a centimeter apart, and over the course of that centimeter, the blood has accelerated by 40%. Just as when making measurements in 2D echo, when using pulsed wave Doppler, there are conventions for sample volume placement that need to be followed in order to allow comparisons between individuals and within the same individual over time. When assessing flow through the LV outflow tract, the sample volume should be placed immediately proximal to the aortic valve leaflets at end diastole. When the leaflets open, the valve is clear of the sample volume, so no opening click is recorded. During systole, the valve is pulled apically, such that when the valve closes, it is now level with the sample volume, resulting in the presence of a closing click. When a closing click is not seen, it may suggest that the sample volume is not placed deep enough within the outflow tract, which will lead to an underestimation of velocities. Remember that when using continuous wave Doppler, we should always expect to see both an opening and a closing click, because the valve will always sit along the path of our ultrasound beam. Next, I would move on to optimizing the position of the baseline, and then the y-axis scale. Here we have pulse wave Doppler of LV filling during diastole. The graph displays all of the information that we might want. However, there is a lot of space that's being wasted which we could use. When making measurements from 2D clips, we often zoom in on the region of interest in order to maximize the precision of our measurement, and the same principle applies here. Sometimes you wish to demonstrate flow in both directions, in which case it's appropriate to leave the baseline somewhere near the middle of the graph. However, when you're focusing on flow in one direction only, then the baseline should be shifted. Here we care about flow towards the probe, and so we can drop the baseline towards the bottom of the graph. The scale can then be adjusted so that the envelope fills the majority of the height of the graph, being careful to avoid clipping the tops of the envelopes. Next, sweep speed should be adjusted. Now there's no single sweep speed which is correct, and it will depend on what you're trying to demonstrate. Here the sweep speed has been reduced to 25 millimeters of screen per second. This allows us to see 11 cardiac cycles, and allows us to appreciate the impact of respiration on LV filling. In general, slow sweep speeds are reserved when we wish to show variation over time, which is often variation with the respiratory cycle. The downside of slow sweep speeds is it makes accurate measurement of envelopes more difficult, and so when this is the priority, the sweep speed needs to be increased to show a few envelopes which can be measured much more easily. In this next clip, the sweep speed has been increased to 150 millimeters per second, which means we now have just under 2 complete cardiac cycles. The impact of respiriphasic variation is lost, but these envelopes could be traced much more reliably. Finally, we adjust the Doppler signal gain. My personal practice is to decrease the gain to a very low setting, but one which allows me to still clearly see the envelope. Measuring an overgain Doppler trace will typically lead to an overestimation of velocities. Alright, so to quickly recap, whenever you're using Spectral Doppler, you should take care to optimize the graphs that you're using to make your measurements. This is the sequence of optimizations that I employ and recommend to my trainees. Now that we can produce spectral Doppler graphs, we need to learn what information this tool can provide us about a patient's circulation. This involves discussion of some of the physics that govern fluids in motion. Now, I'm a clinician working in critical care and not a physicist or a physiologist, and so I only intend to scratch the surface of some of these concepts. As is the case in all of the lectures, the following models will be gross oversimplifications, but I hope that they provide insight that allows you to understand why we can apply these techniques at the bedside. In order to keep this section relevant, I plan to use real-world practical examples interspersed within the theory. So, most obviously, Spectral Doppler tells us about the speed that the blood is moving as it moves through the heart. To understand why this is useful, we need to understand what factors influence the flow of blood and its velocity. Fluids moving through a closed pipe, which approximates the circulation, move along a pressure gradient, from a high pressure to a low pressure. The flow is generated by the pressure gradient, such that when there is no pressure gradient, there is no flow. The flow that is generated is resisted by friction, and friction is proportional to the viscosity of the fluid, the length of the pipe, and is inversely proportional to the fourth power of the radius of the pipe. In critical care, it's common for us to describe the resistance across a large portion of the circulation in order to help understand how the body is responding during states of critical illness. For example, we can use cardiac output monitoring devices to estimate the cardiac output, and use invasive catheters to measure the mean arterial pressure and central venous pressure, which gives us our pressure gradient. When the pressure drop across the non-pulmonary component of the circulation is known, we can calculate the systemic vascular resistance, which is the composite resistance across all of the non-pulmonary blood vessels. There are different units that can be used to describe resistance, but for our purpose I'm going to use Wood's units, which are millimeter mercury minutes per litre, because millimeters of mercury, minutes and litres are all units that we're familiar with using when describing blood pressure and blood flow. If we consider a realistic set of values we might see in a critically ill patient, we might have a mean arterial pressure of 65 millimeters of mercury, a central venous pressure of 5 millimeters of mercury, and so our pressure gradient is 60. Our cardiac output might be 6 litres per minute, so this would give us a systemic vascular resistance of 10 Wood's units. In echocardiography, we can visualize small portions of the circulation as the blood moves through the heart. At this scale, the physics that determine how blood moves remain the same. There are pressure gradients which generate flow, and there is resistance to that flow. Let's have a look at some simple examples which will help us appreciate these relationships. All of these examples will strip away some of the complexities of hemodynamics to allow us to focus on a few core principles. So let's start by imagining we have two tanks connected by a long thin pipe. Tank B contains a large hole on one side, so cannot be filled beyond this point. Initially, the system is filled such that both tanks are level. The pressure across the entire system is equal, so there is no flow. We then start to fill tank A at a constant flow rate. As the tank starts to fill, a pressure gradient begins to develop, with the pressure in tank A becoming greater than that in tank B, and fluid starts to flow from A to B. As more fluid enters the system and the pressure in tank A rises, then the greater the flow rate becomes between the two tanks. Eventually we reach a point of equilibrium. Now the flow in and out of the system is equal, and there is constant pressure gradient between the two tanks. Now if the pipe offers a constant resistance to flow, then if we double the flow into tank A, then we will see our pressure gradient rise to double. And if we halve our flow into the system, then we lose excess volume until the pressure gradient halves. If we reach steady state and then draw a line between our two tanks, we can see a visual representation of our pressure gradient. Interestingly, if we attach a manometer to our pipe anywhere along its length, we see that the pressure at that point is full and proportional to our distance along the pipe's length. This makes sense when we consider that the total resistance offered by two pipes connected in series is equal to the sum of the resistance of each of the two pipes individually. Assuming that the resistance in the first half of the pipe is equal to that in the second half of the pipe, then a manometer placed halfway between tank A and tank B would be expected to register a pressure that is half a pressure gradient. Let's now consider the speed at which fluid moves through this system. As this pipe has the same diameter along its length, fluid will flow at a constant velocity. Let's imagine that the pipe has an internal diameter of 2 centimeters. Then each centimeter slice of the pipe has a cross-sectional area of pi centimeters squared and a volume of pi milliliters. If the flow rate through our system is 6 liters per minute, then this equates to 100 mils every second, which means that in any given second, fluid within the pipe will need to advance approximately 30 centimeters in order to make room for the additional volume that's being added. Now let's take a look at a second example. Let's see what happens if we replace the pipe between the two tanks with one that tapers halfway along its length. So in this second example, the first half of the pipe has the same diameter as that from our first example, but the second half of the pipe is 70% the diameter. This means that the cross-sectional area has shrunk to just under half the original area. Poiseuille's law tells us that the radius has the greatest impact on resistance. And by halving the cross-sectional area, the resistance increases by a factor of 4. In this second example, if we maintain the same flow rate of 6 litres per minute, our total pressure gradient between tank A and tank B increases by a factor of approximately 2.6. Once again, we can draw an imaginary line between the column heads in the two tanks to represent our pressure gradient. We can then insert manometers into our pipes to assess the pressure at those locations. If we place a manometer within the second, narrower section of pipe, it registers a pressure lower than the pressure gradient line. Somehow, increasing the resistance at this point has reduced the pressure. Why is this occurring? So we can define pressure as the perpendicular force acting on a surface. If we imagine a sealed container filled with liquid at rest, then the liquid inside the container will be applying an equal pressure in all directions on the internal surface of the container. If we zoom into the particle level, we can see that the particles within the container are continually moving and in random directions. Sometimes the particles collide with the container's surface, and the pressure is proportional to how often these collisions occur. We can increase the pressure within the container by increasing the frequency of collisions. We could keep the container size the same and add more liquid. Now there are more particles, so collisions occur more frequently. Or we could keep the amount of liquid constant and decrease the size of the container, which would produce the same effect. Or we could keep both the mass of the fluid and the volume of the container constant, but we could heat the liquid, transferring energy to the particles and increasing the rapidity of their movements, and thus increasing the frequency of the collisions, again increasing the pressure. Now let's imagine that our liquid is in a pipe and is flowing from left to right. Now the motion of the particles is no longer equally random in every direction. There does remain some movement in every direction, but on the whole there is more movement in the direction of the flow than in other directions. And so we see fewer collisions with the walls of our pipe. As the number of collisions with the wall decreases, this equates to a decrease in the pressure within the pipe. The faster the liquid flows, the more likely individual particles will be moving in the direction of the flow, the less likely they will collide with the internal surface of a pipe, and the lower the pressure. We can describe the liquid as having both a pressure energy and a kinetic energy. When the liquid is at rest, there is no kinetic energy, only pressure. Assuming that no energy is added to our liquid, then when it is moving, it must have converted some of that pressure energy into kinetic energy. The greater the kinetic energy, the lower the pressure. The law of conservation of mass tells us why the fluid must speed up as it passes from the wider pipe to the narrower pipe. Let's return to our pipe with an internal diameter of 2 cm, which then narrows to 1.4 cm. Fluid is flowing at a constant rate of 100 mL every second. In the first portion, the volume of 1 cm of pipe is 3.14 milliliters. So this means that 100 mL of fluid will occupy 31.8 centimeters of pipe. As each second another 100 mL of fluid enters our pipe, the fluid needs to move along the pipe at a rate of 31.8 centimeters per second. When we reach the narrowing, the diameter decreases by 30%, such that each centimeter of pipe length can only accommodate 1.54 milliliters of fluid. As the pipe keeps accommodating another 100 mL every second, we need to maintain the same flow rate through our narrower pipe, and therefore the fluid speeds up to a velocity of 65 centimeters per second. The fluid has sped up without any energy being transferred to it. Therefore, some of the pressure energy must have been converted to kinetic energy. The pressure must have fallen. This relationship was described by the Swiss mathematician Daniel Bernoulli and later refined by his countryman Leonhard Euler. At all points in our circuit, the total energy is equal to the sum of the pressure energy, the kinetic energy, and the gravitational energy. In our system, the height of the fluid doesn't change, so we can ignore the gravitational energy as we can assume that it is the same on both sides of the equation. When we're performing an ultrasound in our largely supine patients, we can also ignore the contribution of gravitational energy. We can further simplify this equation in order to make it of practical use to us as sonographers. The density of blood in millimeters of mercury is taken to be 7.95, which is close enough to 8 that we can substitute the value of 8 into this equation, which allows us to simplify it further. This equation allows us to estimate the drop in pressure that occurs as velocity increases. In this model, let's imagine that our fluid has the same density as blood. The blood in the first segment of pipe is travelling at approximately 0.32 meters per second. When it reaches the second section of pipe, it speeds up to 0.65 meters per second. If we substitute these velocities into our equation, we can estimate the pressure drop that is associated with this increase in velocity. When we're assessing stenoses within the heart, we typically encounter maximal velocities in the order of between 2 and 6 to 7 meters per second. Contrast this with velocities seen proximal to stenoses, which are often less than 1 meter per second. When we have this situation, where V2 is much higher than V1, then V1 makes such a small contribution to the equation that we can ignore it, without significantly changing our interpretation of the result. Let's imagine that our pipe narrows from a diameter of 2 centimeters down to just 6 millimeters. Now the cross-sectional area has decreased by over 90%, down to 0.28 centimeters squared. Now the fluid flow rate will need to increase to just over 3.5 meters per second. By putting these values into our equation, we can see that most of our information about the drop in pressure comes from our knowledge of the velocity at point 2. Indeed, we could disregard the velocity at point 1 completely and obtain a result with no clinically meaningful difference. For this reason, by convention, when the velocity prior to a stenotic lesion is less than 1 meter per second, we disregard it, and we use the most simplified version of Bernoulli's equation. The pressure gradient is equal to the maximal velocity squared multiplied by 4. What I find really interesting is what happens to the pressure within the pipes if the pipe then widens back to its original width. So let's look at a third model. Again, this isn't to scale, but let's imagine that our first pipe has an internal diameter of 2 centimeters. Then it narrows to a width of 1.4, and then it opens back up to 2 centimeters again. Now, as our fluid passes from the narrow section of pipe in the center to the wider section of pipe, it slows down. Indeed, as the diameter of the first and third sections of pipe are identical, and no fluid has been lost, then the flow rate in the final section of pipe is going to be identical to the flow rate in the first section of pipe. In this example, the fluid slows back down to 31.8 centimeters per second, and as the fluid has slowed down, its kinetic energy has decreased, and therefore the pressure energy will increase. In an ideal scenario in which no energy is lost, then the pressure will rise back to the level that we would have expected if there had never been any narrow section of pipe. This phenomenon is termed pressure recovery. The reality, however, is that the sudden transition from a narrow pipe to a wider pipe will lead to some turbulence, which will result in some energy being lost as heat. The greater the turbulence, the more energy is lost, and the less pressure is recovered. Now, none of these models we have looked at so far really approximate the human heart, so let's try to imagine a model that looks a bit more like the circulation that we will be assessing with echo. Okay, so this isn't perfect, but it gives an impression. So here we have an enclosed circuit where blood is moving from the pulmonary vein on the left to the aorta on the right, through the LA and LV, and through the mitral and aortic valves. Here we're imagining a heart rate of 60 beats per minute, and this model has been slowed down to 20% of normal speed, such that we have one complete cardiac cycle every 5 seconds. No new blood is being added to our system. We're imagining that the circulating volume is fixed. But now flow is occurring due to pressure gradients generated by contractions within the heart. In our model, there's sinus rhythm, so we have initially atrial contraction, followed by ventricular contraction. Our valves are competent and they open well, so blood is flowing in an antigrade fashion with little resistance to flow within the heart itself. So, if we have a phased array probe in our hand, what can Spectral Doppler tell us about this circulation? What clinically useful information can we ascertain? Let's start by calculating how much blood is leaving the left ventricle during each ventricular systole, the stroke volume. To do this, we first need to estimate the cross-sectional area of the left ventricular outflow tract. In transthoracic echo, we do this from a parasternal long-axis window zoomed in on the outflow tract and the aortic root. We measure the outflow tract diameter immediately proximal to the aortic valve hinge points during mid-systole, measuring from inner edge to inner edge. We then plug this diameter into the equation for the area of a circle in order to approximate the cross-sectional area of the outflow tract. When making this measurement, we're assuming that the LVOT is perfectly circular, which in reality is not the case. The outflow tract is usually ellipsoid, with the anterior to posterior diameter being slightly shorter than the transverse diameter. The tract typically becomes more circular when nearing the valve, which is part of the reason why we make this measurement as close as possible to the valve hinge points. Now that we've estimated the outflow tract area, we can imagine a two-dimensional disc of red blood cells sitting at the exit of the left ventricle, waiting to be ejected into the aorta. We can then use pulsed wave Doppler to estimate the stroke distance, how far the disc moves during systole. We typically make this measurement from the apical 5-chamber view, although the apical 3-chamber view can sometimes provide better alignment. We start with a standard 5-chamber view and then manipulate the probe to reduce the angle between the cursor and the direction of blood flow. Often this is achieved by sliding the probe laterally and then rocking the probe back. The sample volume is placed within the outflow tract just proximal to the leaflets during diastole. The pulsed wave Doppler graph that we obtain tells us the speed of the blood as it moves through the sample volume. We can see that the blood speeds up to a maximum velocity and then slows back down, ceasing when the aortic valve closes. Distance is the product of speed and time. By tracing the outer edge of the modal velocity, our ultrasound system will calculate the area under the traced envelope and calculate the distance travelled for us. Here we can see that ejection lasted for 330 milliseconds and had an average velocity of 83.5 centimeters per second. Therefore, we can estimate the disc of blood has travelled 25.3 centimeters. We refer to this as the velocity time integral, or VTI. If we wish to estimate the ejected volume, we can multiply the LVOT area by the VTI. It is normal for stroke volumes to vary beat to beat, in part due to changes in intrathoracic pressure during the respiratory cycle, as well as due to variation in cardiac cycle length. In certain disease states, these normal variations can become exaggerated. In order to find the average stroke volume, we need to make repeated measurements and then average the obtained values. When the patient is in normal sinus rhythm and stroke volume variation is not excessive, we can use as few as 3 averaged beats. When the stroke volume variation is more pronounced, for example in a patient in atrial fibrillation, then we may need to average more measurements, typically between 5 and 10, depending on how great the observed variations appear. One reason to estimate the stroke volume is to calculate the cardiac output. To do this, we simply multiply the average ejected volume by the number of beats per minute. This is something that I do routinely in critical care when assessing shocked patients. But there are other reasons to calculate the stroke volume, and to see one such example, let's move beyond the outflow tract to the aortic valve. So an extremely common pathology that you will encounter time and again when performing echocardiograms is aortic stenosis. We have seen how the blood has to accelerate as it passes through a narrowing, and exactly the same thing happens when the aortic valve is stenotic. The greater the severity of the stenosis, the smaller the hole the blood has to pass through, the faster it must travel. Now we're looking for the fastest measured velocity. We are not concerned with exactly where the velocity arises from, but it's essential that we don't miss it, and the velocity might well exceed 5 meters per second, so far beyond the Nyquist limit using pulsed wave Doppler. And so now we're going to be using continuous wave. Once again, we use a modified apical 5-chamber or 3-chamber view and line the cursor up with the center of the valve. It is essential that we nail the narrowest part of the valve, and so when aortic stenosis is suspected, we should make repeated efforts to obtain this trace from all available views. In an outpatient setting, we might elect to use a dedicated PEDOF probe, which is a specialized probe with a very small footprint, which allows it to get into small spaces such as narrow rib spaces. The trade-off with this specialized probe is that it can't produce a 2D image and so it takes practice to use it effectively. In this model, our valve leaflets are thin and mobile and open fully in systole, providing little resistance to flow, and this is the continuous wave Doppler graph that is produced. Now we can select the peak of the envelope and take note of the maximum velocity that's detected. In this example, it's 1.5 meters per second, and this value isn't particularly high and is consistent with our interpretation of the 2D image, that the valve is working well. Whilst I haven't demonstrated it in this example, just as was the case with pulsed wave Doppler in the LV outflow tract, I should really make multiple measurements and average these to negate the impact of stroke volume variation. Now let's imagine what would happen if our valve were stenotic. Now the leaflets appear visibly thicker and appear to open less well, so we have a heightened index of suspicion. If there is aortic stenosis, then the blood that's ejected will need to speed up several times over if it's all going to get through that narrow opening. Once again, we apply continuous wave Doppler and we obtain this trace, and we can see that the maximum observed velocity is just over 3.2 meters per second. This is despite the fact that the thumbnail shows us that it wasn't possible to obtain perfect alignment of the ultrasound and blood flow, so this value will be an underestimate. 3.2 meters per second is a significant transvalvular velocity and is associated with moderate aortic stenosis. Prior to the widespread availability of Doppler ultrasound, aortic stenosis was investigated in the cath lab where invasive pressure measurements were taken from the aorta and left ventricle, and the drop in pressure across the stenosis was calculated. Whilst this technique is no longer recommended when echo assessment is conclusive, one hangover from this is that it's common to use the simplified Bernoulli equation to convert the measured velocity into a pressure gradient. If we perform that conversion in this example, then we end up with a maximum drop of 42 millimeters of mercury. It's worth noting that echo estimates of the pressure drop and those made invasively will often not correlate perfectly. Now there's a number of important reasons for this, and we're briefly going to detour to look at two of these. First, this can occur due to a phenomenon we discussed earlier, namely pressure recovery. Echo estimates of velocity and hence pressure are made from a point of maximum velocity, which is the vena contracta. This point, where the blood is travelling most quickly, occurs just beyond the leaflet tips. As the blood passes through the stenotic valve, it continues to accelerate momentarily before starting to slow down. Now contrast this with the invasive catheter pressure measurements, which are typically made within the proximal ascending aorta. By this point, the blood has already started to slow down, and so now some of that kinetic energy that hasn't been converted to heat due to turbulence will be converted back to pressure. The pressure in the proximal ascending aorta will be higher than it was in the vena contracta. Another reason why these two different techniques might produce different values for the drop in pressure is the fact that Doppler ultrasound is interested in the greatest pressure gradient observed at a single instant, whilst invasive pressure measurements compare the highest left ventricular pressure and the highest aortic pressure, even if these two values didn't occur simultaneously. This graph shows us a patient with severe aortic stenosis. The light blue line is the left ventricular pressure, whilst the red line is the pressure in the aorta. As the aortic valve is narrow, the blood cannot fill the aorta rapidly, so during the first half of systole, the LV pressure rises more rapidly than the aortic pressure, which has a relatively late peak. We can see in this example how the peak-to-peak measurement is smaller than the gradient in early systole. Current European Society of Cardiology guidelines on the assessment of aortic stenosis with echocardiography put more stock in the mean pressure gradient than in the peak gradient. In this graph, the mean pressure gradient is represented by the shaded area. If we return to our continuous wave Doppler trace, we can see that as we have traced the outer edge of our envelope, then the ultrasound software has measured the velocity at each point along the envelope, converted that velocity to a pressure gradient, and then quoted to us the mean of those estimated pressures. And here that comes out at 23 millimeters of mercury. Again, another value that is consistent with moderate AS. Now, before we started using Doppler to estimate maximum and mean pressure gradients, we discussed how we could use the stroke volume that we estimated using pulsed wave Doppler of the outflow tract to aid us in assessment of the aortic valve. We can do this because the law of conservation of mass tells us that all of the blood that's ejected through the outflow tract will pass through the aortic valve. We can estimate the LV stroke volume and then plug that into the continuity equation to estimate the aortic valve's effective orifice area. the two-dimensional area at the vena contracta immediately beyond the valve leaflets and the true geometric aortic valve area. Rearranging this equation tells us that the estimated aortic valve area is equal to the stroke volume divided by the VTI of our obtained continuous wave Doppler trace. Let's plug the values we've obtained from this example into our equation. So we've measured the LVOT diameter as 1.8 centimeters, which gives us an estimated outflow tract area of 2.55 centimeters squared. With an LVOT VTI of 24.7 centimeters, we estimate the stroke volume as just shy of 63 mils. Now, if we divide this value by our aortic valve VTI of 59.2 centimeters, we can estimate our aortic valve area at just over 1 centimeter squared. Again, a value in the moderate range, and importantly, a value consistent with our 2D and colour imaging. For further practical examples of where we can use spectral Doppler, let's return to our model of a healthy individual and turn our attention to the mitral valve. So, in individuals in sinus rhythm, there are usually two distinct phases of LV filling. Early filling occurs as the mitral valve first opens following isovolemic relaxation, and then additional filling occurs during atrial systole. In health, and when the heart rate is within the normal range, these two phases are separated by a period of diastasis, where very little filling occurs. However, when early filling is delayed or prolonged, especially at faster heart rates, these two phases can overlap. As ever, the flow of blood from the left atrium to the LV is driven by the pressure gradient between the two chambers, and so will be affected by LV relaxation, LV stiffness, and left atrial pressure. In comprehensive echo, assessment of this filling pattern forms one important component of the assessment of LV diastolic function. Now, it's worth saying that this is a huge topic that certainly requires its own lecture, and this talk isn't going to be able to cover this topic in any great detail. However, if you are going to start performing comprehensive echo, then you'll need to start measuring LV filling correctly, alongside developing an understanding of what the different filling patterns signify. We typically assess LV filling from the standard apical four-chamber view. We used pulsed wave Doppler, and we place our sample volume level with the tips of a mitral valve when the valve is open. In healthy individuals with a structurally normal mitral valve, it's usually relatively easy to align the ultrasound cursor with the flow of blood. So this is the inflow trace obtained from our healthy patient. Comparing the recorded envelopes with the ECG trace allows us to identify the different phases of the cardiac cycle. The QRS complex signifies the onset of ventricular systole and isovolemic contraction. Below the baseline, we've captured some flow within the LV occurring during systole, and this will coincide with ejection. Once the ejection has ended, then the heart undergoes a period of isovolemic relaxation prior to the mitral valve opening. And at this point, we first see flow into the left ventricle towards the probe. We refer to this as the E wave, where E stands for early diastolic filling. The E wave terminates when the LA and LV pressures equalize. And then with the next P wave, we see the onset of atrial contraction, and there is a rise in LA pressure, leading to some additional blood being sent into the left ventricle. Viewers paying close attention might also notice the presence of a small amount of flow occurring between the E and A waves. This late diastolic flow is an L wave. It can be seen in patients with a non-compliant left atrium, where pulmonary venous flow is carried straight through into the left ventricle, but it can also be a normal finding in healthy individuals, particularly at slower heart rates, as is the case here. When assessing LV filling, we measure the peak velocity of the E wave and A wave and compare these two values, as well as looking at the E wave deceleration time, the time taken from the peak of the E wave down to the end of the E wave. As I said, it isn't going to be possible to go over all of the possible patterns you might encounter in this lecture, but we can look at a couple of common patterns in order to get a flavour. So this trace is from a young adult with a structurally and functionally normal heart. Here the left ventricle is very good at actively lengthening during early diastole, such that it's able to lower its pressure and generate a decent pressure gradient between the LA and LV. Subsequently, early filling is rapid and the LV fills quickly, such that the first phase of filling is completed early in diastole. When the left atrium contracts during atrial systole, very little additional blood is sent into the well-filled LV. Compare that with this trace again obtained from a healthy individual, but this time a little older, in their mid-40s. To be clear, this is also a very normal trace, however we can see that the E wave has a lower peak velocity than in our young patient. Here LV relaxation is not quite as brisk, but it's certainly adequate. We can also see that the A wave is much more prominent than in the first case, with both the maximum velocity and the area under the curve being comparable to the E wave. A significant proportion of LV filling is occurring during atrial systole. Let's move on to another example. So here we have a lady in her late 70s without any known cardiac disease, who I was scanning because she had a pleural effusion and I wanted to determine if her left atrial pressure was likely to be elevated. Her LV was of normal size with a normal ejection fraction, but her LA cavity was right at the upper limit of the normal reference range. Here we can see that the E wave reaches a maximum velocity of just over half a meter per second. Early diastolic filling is not rapid, and it carries on for much longer than in our previous examples, as evidenced by the extended deceleration time. During atrial systole, the A wave velocity is almost double the E wave velocity. The implication here is that there is impaired left ventricular relaxation. The LV is not good at sucking blood from the left atrium. But the LV walls are not stiff, there's reasonable LV compliance, so when the atrium contracts, it's able to push blood forward into the ventricle. In our fourth example, we have a lady in her late 80s. She has at least moderate aortic stenosis, an element of left ventricular hypertrophy, and a dilated left atrium. The ratio of E and A waves now resembles that in the first case that we saw, with the E wave reaching a much greater maximum velocity than the A wave. In addition, the A wave duration is short, and we have an E wave deceleration time of just over 100 milliseconds. In our first case, the rapid E wave was due to the well-functioning LV being able to quickly lengthen and drop its pressure below left atrial pressure, but it's difficult to believe that the same explanation applies here. This patient almost certainly has elevated left atrial pressure, and the high early diastolic velocities are due to an increased push from the left atrium rather than increased pull from the LV. In addition, this hypertrophied LV will have low compliance, so when the atrium contracts in atrial systole, it struggles to push much more blood forward. That patients with elevated left atrial pressure can have LV filling traces which mimic healthy individuals can sometimes prove a challenge to accurate interpretation of the measurements that we make. It's often helpful to interpret the filling pattern in the context of the speed by which the LV is lengthening in diastole. To do this, we employ a special form of pulsed wave spectral Doppler termed tissue Doppler imaging. When using tissue Doppler, any high velocity but low intensity signal is filtered out. Effectively, the signal returned from blood is filtered, leaving the lower velocities, but greater intensities of the muscle itself. Switching the ultrasound machine to tissue Doppler mode might produce a 2D image that looks a little like this. Here we have a standard apical 4-chamber view, but rather than displaying the heart using a grayscale, it's displayed as red when moving towards a probe and blue when moving away from a probe. We then place the sample volume over the LV wall at the point where the mitral valve leaflet inserts, and we're going to do this twice both at the septal and lateral hinge points. This is the tissue Doppler graph that is obtained when placing the sample volume adjacent to the septal hinge point. Here the annulus is pulled towards a probe when the LV shortens in systole, and this is displayed as velocities above the baseline. In diastole, the LV lengthens and the annulus moves away from a probe, and so we record negative velocities below the baseline. These values that are displayed, around 8 to 10 centimeters per second, are perfectly normal in this healthy volunteer, and we can see how they're quite a bit lower than the blood velocities we've been looking at. Because these velocities are relatively lower, we don't expect to have any issues with aliasing. However, it is important to remember that this is a spectral Doppler technique, and so is vulnerable to all of the other pitfalls that we've already discussed, and it's important to try to ensure the best possible alignment between the ultrasound beam and the angle of motion. If we look at this trace in detail, we can pick out the different phases of the cardiac cycle and see how each relates to our LV filling trace. So first we have this sharp spike that signifies isovolemic contraction, and then we see a sharp positive velocity as LV begins to shorten. LV shortening ends and we enter a period of isovolemic relaxation, and then the LV begins to lengthen, and this coincides with our E wave. There's a brief period of diastasis before atrial systole begins. This graph provides us with information about time on the x-axis and velocity on the y-axis. So if we integrate the area under each of these curves, then it should provide us with distance information. It should approximately tell us how far the annulus is moving across the cardiac cycle. To demonstrate that this really works, we can zoom in on the mitral valve annulus, and here we are over the septal annulus, and use M mode to track its motion over time. We might do this to measure the mitral annular plane systolic excursion, or MAPSE, but if you haven't done this before, then you may well have measured the right heart equivalent, which is the TAPSE. Interrogating the M-mode image shows us that the annulus moves approximately 13 mm apically during systole, moving halfway back during early diastolic filling, and then the remainder of the distance during atrial systole, which is essentially the same pattern that we see in our tissue Doppler graph. When we've obtained tissue Doppler graphs at both annuli, we measure the maximum myocardial velocity during early diastole, which we term E', and then average these two values to find our average E'. We then divide the blood velocity by the myocardial velocity, E over E'. When this ratio is small, it tells us that our muscle is moving quickly relative to the blood velocity and insinuates that our ventricle is good at sucking blood from the atrium. When the resulting ratio is high, it tells us that the muscle is not moving quickly enough to explain the observed blood velocity. The implication here is that the left atrial pressure is high and is pushing blood into the left ventricle. Multiple investigators have looked at the relationship between E over E' values obtained with echocardiography and invasive measurements of intracardiac pressure, either LV diastolic pressures with left heart catheters or the pulmonary capillary wedge pressure as a surrogate for left atrial pressure with right heart catheters. Whilst there's no magic formula that allows you to convert an E over E' measurement into a reliable estimate of LA pressure, there is a good correlation amongst many different patient cohorts, and this is an important measurement that feeds into echo guidelines. There are some important considerations to remember when looking at LV filling patterns. Firstly, I mentioned that E and A waves may emerge at faster heart rates or in certain disease states. Here we have a patient with a known dilated cardiomyopathy whose systolic function has acutely deteriorated in the context of a recent bereavement. Despite the fact that he's not tachycardic, systole is relatively prolonged, in part due to left bundle branch block. Here, early filling is not finished before the onset of atrial systole. The A wave is superimposed onto the E wave. By convention, when the A wave is starting whilst the E wave velocity still exceeds 20 cm per second, we don't measure the A wave. This is another example, but even more pronounced. This patient has developed sepsis and LV impairment following a stem cell transplant. They have only a modest tachycardia, but this combination of relatively prolonged systole and fast heart rate make the E and A waves almost indistinguishable. Secondly, it's important to remember that this relationship of E wave followed by A wave may not always be present. Here we have an elderly gentleman in atrial fibrillation, and so naturally A waves are entirely absent. In this next trace, we have a patient receiving RV pacing via temporary pacing wire for complete heart block following an MI. Here we can see regular broad QRS complexes, which match his paced rate of 69 beats per minute. However, he still has atrial activity, which we can pick out on his ECG, and so we can see that there are A waves with an atrial rate of just over 90 beats per minute. But there's no consistent relationship between the E waves, which follow ventricular contraction and so track the pace rate, and the patient's native A waves. When we previously looked at transaortic flow, we used continuous wave Doppler to help grade aortic stenosis, and we use a similar technique to help assess stenotic mitral valves. Staying in our standard apical four-chamber view, we place the cursor through the center of the orifice and, as best we can, align with the direction of blood flow. This is the trace obtained from a gentleman with rheumatic mitral valve disease. He has only mild MR, and the dominant lesion here is mitral stenosis. We can see in this trace a very high initial velocity across the valve of almost 2.5 meters per second, so his left atrial pressure must be significantly elevated. When we looked at a previous example of a patient with elevated left atrial pressure, the early filling rapidly terminated as the high pressure forced blood into the LV. But in this patient with mitral stenosis, the blood can't pass through the valve quickly, and so LA emptying is protracted. LA pressure remains high, as does the pressure gradient. The preferred method for assessing the severity of the obstruction is to measure the mean pressure gradient across all of filling, from the opening of the valve to its closure. Now, it's not uncommon for patients with mitral stenosis to develop atrial fibrillation, but this patient happens to be in sinus rhythm, so we can measure the mean pressure gradient from the start of the E wave to the end of the A wave. And in this case, we obtain a value of 8 millimeters of mercury, which would be consistent with a moderate stenosis. This measurement is sensitive to heart rate. The pressure gradient is always greatest in early diastole. If the heart rate increases, then the filling time falls, and we lose the relatively lower gradients at the end of diastole, and see only the higher gradients of early diastole. Our measured mean gradient will rise. For this reason, it's important to always quote the heart rate at the time the measurement is made. Another way to describe the shape of this continuous wave Doppler envelope is the pressure half-time. In invasive hemodynamic studies, it was found that there was a good correlation between the clinical severity of mitral stenosis and how long it takes for the LA and LV pressure to equalize during diastole. Here we have overlaid traces from the LA, which is highlighted in red, and the LV, which is in black. The grey shaded area shows the difference in pressure between the chambers during diastole. Investigators measured the pressure difference at the onset of diastole and then measured how long it would take for that pressure difference to fall to half the original value, the pressure half-time. We can use echocardiography to approximate this measurement. This trace was obtained from a different patient who also had rheumatic mitral valve disease, and by chance this patient also had a mean pressure gradient of 8 millimeters of mercury. If you look closely at these envelopes, you can see that there's an initial rapid deceleration which then levels off. This doesn't always occur, but when it does, we ignore the initial steeper portion of deceleration and imagine that the shallower deceleration extended back to the beginning of the diastole. So in this patient, we would start by placing our cursor here, and then extending our line to the end of LV filling here. The ultrasound software will then imagine that the line extends all the way to the baseline. The ultrasound software measures the velocity at the start of the line and uses the simplified Bernoulli equation to convert this into a pressure gradient. In this case, our starting velocity is 167 centimeters per second, and so our starting pressure gradient is just over 11 millimeters of mercury. Now the ultrasound software halves the starting pressure gradient and converts this back to a velocity measurement. If we rearrange the equations ourselves, we realize that for any given starting velocity, a drop in velocity of 29.3% is equivalent to a halving of the pressure gradient. So our starting velocity was 167 centimeters per second. So if we take off 29.3% of that value, we end up with 118 centimeters per second. The software then finds this point along the line and measures the time between those 2 points, which in this example would be 207 milliseconds. A pressure half-time of greater than 220 milliseconds would be suggestive of severe mitral stenosis. When we use pressure half-time to assess mitral stenosis, a shallow slope infers a greater degree of severity, because the narrow valve opening provides resistance to flow and the diastolic pressure gradient from LA to LV is maintained. We can use this same measurement to assess aortic regurgitation. In AR, if the defect is small, then it will produce resistance to flow. The diastolic flow rate from the aorta back into the LV will also be low, so the pressure difference is maintained throughout diastole. Mild AR will produce a shallow slope and a long pressure half-time. Contrast this with the situation in severe AR, where the large defect allows a large volume of regurgitant blood flow. The pressure in the aorta rapidly falls, and the LV diastolic pressure rapidly rises. The pressure difference narrows, and the velocity of the flow between the aorta and the ventricle slows down. If AR terminates prior to the end of diastole, this implies that the aortic and ventricular pressures have equalized. Let's look at two examples. First, we have a middle-aged gentleman with dilated cardiomyopathy, perhaps secondary to anorexia. He has visually mild AR on color Doppler. He's in sinus rhythm, but with very frequent atrial ectopics, and so has an irregular heart rate and a variable duration of diastole. The continuous wave trace shows a relatively flat peak for each of these Doppler envelopes, but the easiest to measure will be this fourth envelope. Here, the pressure half-time comes out at 713 milliseconds. Now let's take a look at this young lady with chronically dilated aortic root and a subacute aortic dissection with severe AR. She was scanned during the COVID-19 pandemic, hence ECG leads weren't used. But these are diastolic continuous wave Doppler envelopes of her AR from the apical 5-chamber view. We can see her slope angle is greater, and we measure her pressure half time at just 143 milliseconds. It is worth remembering that as we can manipulate the scale of both the x and y axes, we can manipulate how the angle of the slope appears on the screen, so it's important to make the measurement rather than just eyeball. This third trace is from a gentleman with degenerative aortic valve disease. At first glance, the slope of his AR deceleration is much steeper than our young lady with an aortic dissection. But this is in part an illusion, due to the fact that the sweep speed is slower, and we're using a different velocity scale. And in reality, the two patients have a similar pressure half time. The continuous wave envelope can also be of use to us in evaluating mitral and tricuspid regurgitation. Firstly, we can assess the intensity of the returning signal. Assuming we've been careful not to overgain our graph, then when the envelope is dense, it's because the volume of blood that is regurgitant is large, and so there are a lot of red blood cells available to reflect sound back to the transducer. When there isn't much regurgitation, then not a lot of blood will be reflecting our ultrasound waves, and our Doppler envelope is faint. Here we have a patient with mild tricuspid regurgitation, and when we place our cursor through what we believe is the centre of a TR, we obtain this faint trace that's difficult to fully discern. The vena contracta will be small, and as the heart's position in the chest is moving with respiration, we don't always line up through the vena contracta and the TR jet. Sometimes the TR is barely captured. Compare that previous trace with this patient with moderate to severe MR. We can clearly make out each Doppler envelope, and they appear more filled in. The shape of the envelope also provides us with useful information. This trace is from a patient with long-standing dilated cardiomyopathy. The onset of MR starts with the onset of ventricular systole and precedes aortic valve opening and the start of ejection, and it continues beyond the closure of the aortic valve through isovolemic relaxation until the mitral valve opens again. The peak of the envelope is said to have a parabolic shape, that is, it is roughly U-shaped and symmetrical. Relatively rapid flow continues throughout all the systole, and this MR is chronic, and the left atrium is dilated to accommodate the additional volume. Contrast that with this next patient who has suffered an acute papillary muscle rupture complicating a posterior ST elevation MI. Her windows were challenging, but you can just make out a flail posterior mitral valve leaflet with eccentric MR directed under the anterior leaflet. This is an acute lesion, and the LA hasn't had time to dilate, and so cannot accommodate the additional volume easily. Left atrial pressure rises sharply, and the velocity of the MR quickly peaks and then slows down again. This produces a triangular envelope with an early peak and then a gradual deceleration. This pattern suggests that the incompetence is either acute or very severe indeed. A common misconception amongst individuals first learning to assess incompetence of the atrioventricular valves is that the maximum velocity of a regurgitant jet is a marker of the severity of the lesion. That because the Vmax is high, then the lesion is severe, and this isn't the case, at least not directly, but it can sometimes provide us with useful information. It's generally less useful in mitral regurgitation. Let's consider why. In MR, the pressure gradient driving the regurgitant flow is the difference between the left ventricle and the left atrium. Assuming there is no stenosis of the aortic valve or outflow tract, then we know that the LV pressure will approximate the systemic systolic blood pressure, which we could measure with a simple blood pressure cuff. It's tempting to imagine that if we know the peak velocity of the MR, then we could apply the simplified Bernoulli equation to this measurement to obtain the pressure gradient, and then subtract the pressure difference from the systolic BP to obtain the left atrial pressure. However, while some investigators have shown good correlation between MR Vmax and invasively measured pressures, there are some limitations that prevent this technique from being recommended. Whilst we won't go into all of these limitations, let's consider a few of them. Firstly, non-invasively measured blood pressure has imperfect correlation with invasively measured pressures. Secondly, our measurement of MR Vmax will also suffer from a degree of imprecision. We may underestimate the velocity due to malalignment, or we may overestimate due to overgaining. As MR is typically very fast, and within the Bernoulli equation the measured velocity is being squared, then any measurement error will be amplified. And thirdly, we're using a big number to hone in on a small number, where small differences in the end result are clinically meaningful. By way of an example, let's imagine we have a patient whose peak LV systolic pressure is 120 mm of mercury, and their simultaneous left atrial pressure is truly 11 mm of mercury, which is towards the upper limit of the normal range. Then, using the simplified Bernoulli equation, we would expect the peak MR velocity to be 522 centimeters per second. What would happen if we tried to estimate the left atrial pressure, but we had some entirely realistic measurement errors? Well, in one meta-analysis that looked at blood pressure cuff accuracy, they found the mean difference between the cuff measurement and the invasive measurement was 8 mm of mercury. So let's imagine that our cuff overestimates the systolic blood pressure as 128. Now, we've been careful to gain our Doppler trace correctly, but we're malaligned by 15 degrees, and so we end up underestimating our velocity by just over 3%, and we measure the Vmax of 504 centimeters per second. This would lead us to conclude that our left atrial pressure is 26, which is very significantly elevated. What about if our measurement errors were in the opposite direction? So we measure our systolic blood pressure and we get 112, and we measure the MRV max and we're slightly overgained and we get 5.4 meters per second. Well, then we'd end up with a left atrial pressure of -5. So an attractive idea that falls down in practice, at least in my hands it always does, and it doesn't feature in the guidelines. Using TRV max to draw conclusions about the pulmonary systolic blood pressure does feature in the pulmonary hypertension guidelines, but this technique is complicated by a similar set of pitfalls. In theory, we can add the Bernoulli equation-derived estimated pressure gradient to the right atrial pressure to estimate the right ventricular systolic pressure, and if there's no stenosis of the pulmonary valve, then we can use this estimate for the pulmonary artery systolic pressure. Firstly, we need to start with a value for right atrial pressure. In critical care, it's common to site central venous catheters in the internal jugular or subclavian veins, and for the tip to sit at the entrance of the right atrium. If we transduce this catheter and obtain a reliable waveform, we might choose to substitute this measurement for the RAP. Of course, the vast majority of patients undergoing echocardiograms won't be undergoing invasive hemodynamic assessment, and so then we need to have a guess at the right atrial pressure. There are published algorithms that advise sonographers on what value of RAP to guess, based mostly on the size of the IVC and the caliber change over the course of a respiratory cycle. But these algorithms are inadequately accurate in practice, and so begin to introduce error. Next, the estimation of a pressure gradient using a Bernoulli equation is also subject to both overestimation and underestimation for the reasons we've previously discussed. When tested in the real world, echo estimates and invasive measurements correlate reasonably, but with inadequate precision to hang your hat on the absolute value. Instead, BSE guidance is to use the TRV max as part of a broader echocardiographic assessment to determine whether pulmonary hypertension is likely or unlikely. Now, a word of caution: when TR is free-flowing, then the pressure generated by the right ventricle is rapidly transmitted back to the right atrium. The lack of a sustained pressure gradient means that relatively low TR maximum velocities can be seen in patients with pulmonary hypertension. This patient, for example, has dilated cardiomyopathy with severe biventricular impairment and dilatation of all four cardiac chambers. His TR trace is triangular rather than parabolic, demonstrating the severity of the TR. Velocities are low, but it would be hasty to conclude that he has a normal pulmonary circulation. Okay, so I think it must be time to wrap up this lecture. I hope you now have enough of an understanding of how spectral Doppler graphs are produced to begin integrating this technique into your practice, and you have some practical examples that are regularly performed in a standard comprehensive echo to get you started.